Hello, I'm Mike McCulloch. Today I'd like to talk to you about a new paper that I've just seen, which is involved with the controversial topic of cold fusion that I covered in a previous video. But cold fusion itself, this topic was started by Pons and Fleischmann back in 1989, and what they did was they took a lump of palladium, and using electrolysis they saturated it with deuterium, which is heavy hydrogen, and then they left it for a while, and they found that some of these samples started to produce heat, and they started to produce more heat than could be accounted for chemically. So they speculated that some kind of fusion was going on. But this caused a lot of controversy at the time because protons were not seen coming off, which they should have been if there was standard style fusion going on. So the topic became very controversial and kind of died down a little bit, although some people have continued working on it. So I became interested in this way back in about 2018, and I published a paper showing that quantized inertia could predict cold fusion under these circumstances. So this is how you do it. You start, as so often, with Heisenberg's uncertainty principle. So the uncertainty in momentum times the uncertainty position, delta p delta x is h bar over 2, which is just a very small constant. And then we know that E is momentum times the speed of light. So you can put that in here. So we get delta E is equal to h bar c over 2d, where d is the dx, the size of the space we're considering. And this formula means that the more we shrink the available space of objects down, so we reduce d, the more energy is going to appear in that cavity. And this is because this is a basic precept of quantized inertia, that you can't have underwaves that are larger than the space that you're in, whether this is the cosmic horizon or a metal cavity. They're the same. The cosmic horizon precludes waves longer than itself. So does a conducting metal cavity, because electrons move in the walls and cancel under waves unless they have a node on that wall, that cavity wall. So this means that if you have a very small cavity and you shrink it down further and further, then the electrons in the walls must accelerate to such an extent that they see under waves that are shorter than that cavity. So that means there must be a lot of acceleration going on in this small area, and also a lot of under waves. And this means that you get a lot of temperature. It will be hot. And we can work out the temperature by using the formula that the energy is equal to 3 over 2 kT, where K is Boltzmann's constant and T is a temperature. And if we put that in the formula, we get this one, which tells you that the lower or the smaller the diameter of the cavity is, smaller d is, the greater the temperature will be. And so I argued that in this paper, that if the palladium contained very small cavities, and given this equation it'd have to be down at about 28 nanometers in diameter, then you would get temperatures high enough that fusion could be produced between deuterium. So I published this in 2018 in Progress in Physics, but a few days ago I noticed a new paper being published that have kind of looked at this. It's by Karahadian et al. And what they did was a very clever experiment. They, like Pons and Fleischmann, they had a block of palladium and they saturated it with deuterium. They slowly saturated it with deuterium, so all the interstices of the structure were occupied by deuterium. That could be. And then they looked for protons coming off, and they didn't see many, because there wasn't much fusion going on, of course. But then they tried to initiate fusion by firing deuterium ions at the block. So that's shown here. So they fired them with various energies, and for large, high energy ones, 6 kilo electron volts, they saw some fusion, but that was expected because there's a theory that electrons within the structure can get between the two deuterium nuclei and help to cause fusion. You see, the problem with fusion, and the reason you need high temperatures, is that deuterium is positively charged, so two atoms of deuterium tend to repel each other. So you need a lot of temperature to cause them to jitter and ram into each other at random. So what was happening at the high energies is the deuterium came in at 6 kilo electron volts, and with the help of electrons in the structure, which get between the deuterium atoms and suck them together, fusion was able to occur. But this model does not occur when you slow down the incident deuterons, the ions. So they did that, and they slowed them down, and they noticed that below about 2.5 kilo electron volts, as they slowed them down, the fusion decreased, but then it plateaued out below about 2.5 kilo electron volts. The fusion was still happening, even though there wasn't enough energy to slam the deuteriums into each other, counter to their repulsion, their self-repulsion. So this implied that some other process is helping the deuterons to fuse. And in the paper they go into a few possibilities, such as this electron screening that occurs. You can get electrons between the deuterons which pull them together. But they say in the paper that they're not sure how this happens. Well, I think perhaps quantized inertia can produce this, as I've explained. This is quite a change, actually, because for the very lowest energies of these projectiles that were firing at the palladium, the amount of fusion was about 10 to the 18 more than they expected. So that's a huge difference. And also this would mean that if we can get fusion this way, it'd be a much cheaper way to do it than building huge magnetic tokamaks and things like that. Okay, so I hope you've enjoyed today's short, and I look forward to speaking to you tomorrow. Goodbye.